I'm Jonas. I'm a postdoc at QuSoft. You may have known me from, the before 4 times. And I'm going to talk to you about something that I've work that I've been working on for the past year or so, mostly with Ingo Roth, who is a PhD student in the ICERT group in Berlin, and Emilio Onorati, who's a postdoc at Imperial. And this is, you can think of this as sort of a cleanup effort. So the title of the talk is a randomized benchmarking mother theorem. And really the goal of what we're trying to do is not so much invent like new protocols as in gather a whole bunch of things together and see where they, how they fit in some sort of unified framework, and try to prove general theorems that hold for everything that we can think of. So I'll first have to tell you what randomized benchmarking is. So I'll start with sort of a little history lesson. So randomized benchmarking, you probably have heard of it, at least sort of by osmosis. It is an experimental technique for estimating error rates in quantum computers. And it's sort of the standard technique, in the sense that if you have heard in the past someone say, oh, my qubit has X fidelity or Y error rate, therefore it's better than someone else's qubit, the number that they're talking about is almost always obtained by a version of randomized benchmarking. And so there are literally hundreds of experimental papers that use a variation of this procedure, and all of them are sort of slightly different. But it came to being now like slightly under 15 years ago when Manny Knill wrote a really nice experimental paper where they sort of put the first pieces of this protocol in place. And I'm going to show you what sort of the essential pieces are later. And this worked, and they observed that it worked in practice, and they could extract some sort of error rate, but there was very little sort of theoretical justification to sort of show what they were doing would always work. And at the same time, there was a concomitant theoretical proposal coming out of Waterloo, mostly by Joe Emerson, but also some other people, which was precisely the opposite thing. It was very well grounded, and that you could guarantee under sort of a wide range of scenarios that the thing that comes out of this procedure is some sort of average fidelity, like some number that you would care about. The problem was that the protocol that they proposed involved taking sort of full-fledged Haar averages over the entire unitary group, which, as all of you know, isn't a very practical thing to do, because most unitaries, or even like if you want to approximate a generic unitary, you need to make an exponentially long circuit. So this was somewhat unpractical. And then sort of the real sort of magical moment came a few years later when Magasan, Gambetta, and Emerson realized that you could replace those Haar averages with just averages over the Clifford group. And I'll tell you why all of these averages work, why they're needed later. But for now, think of them just as sort of little pieces that you can move in and out. And removing these Haar averages and replacing it with Cliffords made something that was really impractical to something that could actually be done. And, now we do these kind of things all the time, right? It's called design theory, and we're sort of blasé about it. But 10 years ago, this was sort of vaguely sort of a small revolution in experimental techniques. And after that, this sort of mini field sort of exploded, especially on the experimental side, but also on the theoretical side. So in the last 10 years or so, people have written up at least 100 experimental implementations of this. This is really the standard protocol. But there's also 35 or so, I think it's 37 on my last count, variations of this protocol, where people say like, oh, we have this little box and it has a bunch of moving parts. Let's take out a moving part and put another one in. This was a really Really great way to write papers about 5 years ago. So you could just take randomized benchmarking, plug something else in, and you have a paper. This has sort of died down a little bit, but with all of these variations, there was a lot of sort of disagreement on how to interpret the output of all of these things and what precisely the limits of validity of this thing are. Because very often people sort of generalized without proving that in this new framework, the same sort of guarantees would hold. So within this sort of little Cambrian explosion of protocols, there was a whole bunch of confusions that arose, and there was a couple of particularly contentious conferences where people sort of shouted at each other about what assumptions you needed to make on the quantum computers in which you run the protocol in order to get sort of sensible output, how to interpret this output data, because like for the basic case, it was sort of clear, but once you started making all these variants, everything got really complicated. And there was like people claiming that it, like randomized, like one of the key points of randomized benchmarking is that it's scalable, so you can do it on a lot of qubits. But like what precisely the limits of this scalability are was sort of unclear. And it sort of varied with all of these protocols, and everything got really confusing, and everything still is really confusing. And then there's a whole bunch of post-processing things that I'll get into later. And so what we wanted to do, and what we've been trying to do for the past year or so, is basically take all of these protocols and gather them into a single sort of meta procedure that encompasses everything we know, and hopefully also a whole bunch of things that we don't know. So you can also think of this as a framework for constructing new protocols. And then for this meta protocol, which consists of a data gathering procedure and a data processing procedure, I'll talk about those later, we want to write down a single sort of theorem that for this meta protocol, we want to guarantee that it works the way it's supposed to do. And we want it to work for all of these possible, like as a consequence, we want to sort of guarantee the validity of all of these known protocols. And we want to sort of do this in the broadest possible sense. We want the weakest possible assumptions for the strongest possible conclusion. And I'll show you how we do that later. And then we also want to give like a really, so sort of basically, if you write down this mother theorem and you interpret everything correctly, you get a really nice way to do, sort of interpret the data that comes out of your procedure as well. You sort of get it for free, but I'll talk about that later. So what is a randomized benchmarking protocol? In particular, what is all randomized benchmarking protocols? Well, it starts with input data. So when you do randomized benchmarking, and again, this is a thing that people like, what I'm putting on this slide right now is like back in the day, this was a full paper. So what you specify is the following 6 things. You take some finite group out of the subgroup of unitaries on Q qubits. The paradigmatic example here is that you take the Clifford group, but you could also take the Pauli group or some other complicated thing, and people have cooked up many varieties. But the point is that you take some finite group, and then you specify some sort of notion of idealness. So you pick a reference representation. And in almost all cases, this reference representation is just a standard circuit representation on your density matrices. So it's just the thing that takes your quantum circuit, takes a density matrix and sends it to U rho, U dagger. So this is sort of the standard, like the thing your quantum computer should be doing. And then you have to specify a few other things. Like another thing you specify is some POVM, like the thing that you're going to measure in the end, and you specify some initial state, or in any case, you specify some ideal versions of these. And then you also specify a set of sequence lengths, which doesn't really matter right now. It's a bunch of integers. These are usually the same for everyone. And then critically, you also specify an end gate. And in almost all procedures, this is going to be the identity, but sometimes it's not. Sometimes it's something else. And then you go to your quantum computer, and your quantum computer provides you with a sort of your basic object of study. Like if you tell it to, you can tell it to implement these circuits, and it's going to not implement these circuits perfectly. It's going to implement them somehow imperfectly, and you can model this imperfectness by saying, oh, I assign to every one of my group elements some quantum channel. So this x2 to the q is sort of the set of super operators. So there's some quantum channel that is associated to the unitary. And this might be your original unitary plus some depolarizing noise. It might also be something else. But we're just going to like look at this sort of abstract object called an implementation map that, that maps the group to some super operators. And this is really the thing that we want to study. We want to learn something, like learning how well your quantum computer performs is really just learning something about this implementation map. And then what randomized benchmarking provides you, or should provide you in general, is some list of probabilities associated to these sequence lengths, small m, that are in this set, big M. So you get some probabilities for each element of your POVM, or at least some estimates. And like you've specified this end gate. And really this also depends on the initial state, but it doesn't really matter. So I'm gonna suppress that in here. And then the way you do randomized benchmarking, the way you do all the randomized benchmarking protocols, given all of these procedures, it looks like this. You take your initial state, you prepare it on your quantum computer, and then you sample M, where M is some integer in your sequence length set. You sample M gates from your group, and you implement them using your implementation map. And this is really just you telling the computer, do a Hadamard gate, do a phase gate, do a Pauli X gate. And you do M of those. And then what you do within this group, you can compute inverses. So you take G1 to GM, and you compute classically the inverse, like the total inverse, so G1 to GM inverse. So the thing that takes you back to the identity, essentially. And then for good measure, you sort of add this ending gate there. So, and then you implement that thing using your implementation map. And we're not going to talk about how hard it is to actually compute this inverse. This is non-trivial, but somehow we're going to assume that we have an infinite amount of classical computation on the side, just to like make everything easier on ourselves, because we're gonna have it hard enough. And then we measure using our POVM, and we repeat this a bunch of times to gather some probability, some estimates for these probabilities. And then we do this for a whole bunch of random selections of these G1 to GMs. So now here I've written down sort of an average over all of these G1s, but in practice what you do is you would take some estimate and you wait for the law of large numbers to kick in, get some good estimate of P rho G of M. And okay, cool.
What is the G inverse of?
Oh, the G inverse is the inverse of, oh, I should have written this down explicitly. It is a G1 to GM, the product, okay, and then the global inverse of that. So what you should think of,
not the inverse of G in particular, right? I mean, it's not the inverse of the G that follows.
Sorry, I didn't quite hear that.
No, it's just, there's also a G right next to it, but the G inverse is not an inverse of the G that follows, right?
No. The G is this sort of this end gate. So the idea is the following. You make some sort of random walk in your space of unitaries. So you apply a gate, you apply a gate, you apply a gate, and then you walk back to the identity in the ideal case. And then sometimes people find it useful to then apply another extra gate, G, which is just specified in advance. Like it's probably easier to think of this end gate as just being the identity, so you do nothing there. And then really what you're doing is sort of in the ideal case, you perfectly invert what you've already done. So you take M steps and then you walk back. And it's sort of important that you compile this because you need to do this in one step somehow.
So DM is G?
No. He makes a long detour and then he implements a G at the end.
Yeah. So you do a long loop and then you implement G. So yeah, this is a little bit abstract, but it's sort of necessary because we wanted to capture all of these possible protocols. So an example of this is if you could, for instance, pick G to be the Clifford group, and the end gate here, the small g, to be the identity. And what you're then doing is you're making a random walk in the space of Clifford gates, but at the end you always end up at the identity. But you make these sort of the walks, you can vary the length of this walk with M. And this, like the fact that you can vary this M is really important. So you choose a whole bunch of different M's and you get data for all of these M's. And then
I'm still confused because what is this G inverse? That is the inverse of the protocol of the inverse of G1 times G2 times GM.
Yes. Yeah. So G1, G2, G3, all the way up to GM.
So this whole thing is computing the identity in the ideal setting.
Yeah.
And then, but then I'm not sure where this end gate G comes in.
Oh, so you do it at the end. So just think of this end gate as being the identity at this point.
Fine, but what do you mean at the end? At the end, does it sort of stick? So it's not the GM. It's not GM.
The thing is, sometimes we want to do walks that end at a fixed point that is not where you started. So you do a walk and the inverse brings you back to where you started, but sometimes you want to end up somewhere else. You want to end up at the global Hadamard rate.
So you do f of g, phi of g, sorry, after or before, depending how you write it, the phi of GG inverse.
Yeah. So you compile this this global end gate. You compile it into the inverse. So it's important that it's sort of in phi.
Okay, got it. Thanks.
It can't add any extra noise. This is a sort of an important detail, which is kind of tricky to do in practice, but people want you to do this. So
Jonas, do I understand correctly that ideally phi is a homomorphism?
Yes. Yeah. So this is a thing that we're going to get to, is in the ideal case, phi is actually going to be a representation of G.
Good. Thanks.
Yeah. So this is sort of the picture that we're going to get to, is that in the ideal case, we're going to be able to somehow analyze this thing using representation theory.
Jonas,
yeah.
Can I ask a question? Maybe there are some. So the idea is to do GG inverse with as little gates as possible, or I mean, you could obviously also just do the inverse of the entire circuit, gate by gate, but maybe kind of feel that's not what you want to do.
No, so it's sort of, this is sort of a technical detail that I'm glossing over. It is indeed important that G inverse is sort of asymptotically independent of M. So basically that you compile it down. So an explicit, a good example of this is, let's say you can implement elements from the Pauli group. Then you do M Paulis. But then if you compute all of them together, it's still a Pauli group element. So you can sort of do it in one step at the end. You just have to figure out what it is.
Yeah, otherwise you would introduce noise again in this kind of step.
Yeah.
That's not what you want.
And it's like it's important that if you take M large enough, that the size of G inverse becomes negligible. And this, like what is a good M sort of scales with the number of qubits. Often it gets a little bit tricky. But this is something I'm going to try not to talk about. So there's lots of things that I'm sort of sweeping under the rug here, but
Jonas?
Yeah.
I also have maybe a stupid question. So is there a difference between applying the last step phi G inverse by replacing phi G and phi G inverse? So why you combine these two gates together and apply?
Oh yeah, this is important. It's important that the G is also sort of compiled in. But if you want, you can just think of it as being applied at the end. It's only important for some awkward technical reason that we're probably not going to mention.
So it's different with applying phi G inverse separately.
Yes. But as long as you consistently compile it in, it's fine.
Can I ask a question?
Yes.
Just sorry, another one. So wondering, like, it seems that if your phi just compiles everything down to the identity, then somehow that seems like you cannot distinguish this from actually
This is the thing I'm going to get to. So now we want this thing. So this is the point that I'm going to make, is that we want this thing. We want to somehow have this data be relevant, and we want to know what sort of the conditions we have to impose on phi are, such that we get sort of relevant data out. Because indeed, sort of a trivial scenario is that you just send you don't do anything. You send all of your gates to the identity, and then all of your data is going to be perfectly flat. Like, you're going to have really nice sort of probabilities, but you're doing really bad gates. So, and you have to make some assumptions on the shape of phi in order to avoid these sort of scenarios. All right, so the claim that people make every time in a randomized benchmarking paper, after they've picked a group and they've picked some gates and they've picked some POVM, they then claim that this data, this P of now the important element here is M, is that this data approximately behaves as a linear combination of exponentials, where the lambdas here, so the k rates of the exponential, only depend on the gates that you implement. So you can sort of, by varying M, you can tell something about this implementation by sort of doing an exponential fit. And in particular, these lambdas, they should correspond to sort of, like, you should get one lambda for all of the sub-representations of your reference representation. So if, for instance, in the Clifford case, you have two irreducible sub-representations in your reference, one of them should give you a number that corresponds roughly to sort of trace loss, and the other one should give you a number that corresponds to the average fidelity. So the sort of extra folklore claim is these lambdas actually sort of determine the average fidelity of your gates. I actually think that there is a better interpretation of this that we'll sort of get for free later. But the point is, this thing, it clearly doesn't hold all the time. So as Jonas said, you can have your gates just do nothing, and then your data will not look like this at all. But you can also have your gates you can have them do some arbitrary behavior, and you might get data that doesn't look like a linear combination of exponentials at all. It might look like something much more complicated. So people usually sort of wave their hands and they say, oh, as long as the gates in your implementation are close enough to what you wanted to do in the ideal case, so this reference implementation, so the idea that your noise is somehow low enough, then this should work out. The problem is that close is a really vague term. And it's sort of not really clear what the limits of this are. In particular, if you're allowed to choose sort of really funky groups and really funky POVMs. So we want to justify this close, and we want to make it somehow rigorous. And the way we're going to do that, we're going to do it in a very particular way that also gives a really nice interpretation of what randomized benchmarking is sort of actually doing. And
Jonas, can I ask a question?
yeah.
What do you mean with the sum over sigma is in omega?
Oh yes, so it's what I mean by this sort of sigma inside here. This is very unfortunate. I mean that, so for every irreducible sub-representation of your ideal representation, you should get exactly one lambda. So it sort of ranges over. So somewhat of an awkward notation, but I've never actually seen a better one.
Okay, thanks.
So it turns out that this sort of complicated randomized benchmarking procedure that we wrote down, where you apply a bunch of gates and then you do a global inverse and then there's some end gate, it turns out that there is a very nice way to rewrite this sort of composition of superoperators using convolutions. So I'm going to define a notion of convolution on these implementation maps. So if I have two maps from a group to superoperators phi and psi, I can define sort of a convolution in the usual way. So this is sort of the standard definition of convolution. And it turns out that you can write your RB operator. So this is apply G1 to all the way to apply GM, and then do the inverse and add some gate in the end, and then sum over all of these things, like take the average. It turns out that you can write this with like a little bit of clever change of variables. You can write this as the m-fold convolution of phi evaluated at G. So this is again a function from the group to the superoperators. And you can sort of perfectly write your probability data that comes out as the m-fold convolution of G sandwiched between your initial state and your final POVM. And here these kets sort of indicate, these are actually sort of matrices. So I'm putting kets around my matrices because I want to vectorize everything, because I'd really like to think about my superoperator as matrices and as my matrices as vectors, because it just makes my life easier. So you're gonna be seeing this notation here for a bit, but it just means that I'm taking some density matrix and I'm applying a bunch of superoperators to it, and then I'm taking the trace. So this is a trace inner product.
Jonas?
Yes?
Should the normalization be the size of the group raised to the power m here?
Yes, yeah, so I forgot a power m here. That is indeed correct. Otherwise it does not work.
Jonas?
Yeah?
Why do you care about representations? Why? So you want to test that your channel behaves in a certain way. Why is it good if it behaves like a representation of a given group?
Because like you can think of a quantum computer. If I apply circuits in a quantum computer and these circuits have a finite group structure, then what I'm implementing on the quantum computer is precisely a representation of that group. Mm-hmm. So in particular, it's sort of the U dagger representation. Mm-hmm. It sort of naturally comes up.
I see. And that's kind of the only behavior you think is natural to study.
No, not necessarily, but it's sort of like the reason we think about representations is because if you read all of those randomized benchmarking papers, every one of them talks about representations of groups. It's just sort of,
well, algebraically it's very convenient because there's lots of tools you can toss at it. But I'm wondering
so this is like basically
where it may not be the natural thing.
Yeah, that is certainly correct. Okay. So, and I think, there is probably a good reason why people always pick groups is because you can actually toss these tools at it. And in particular, one of the things you can do, and I'm gonna sort of go over this a little bit lightly because I think I'm running out of time already. Oh no, I'm fine. One of the things you can do if you have a convolution over group functions is that you can define a Fourier transform because you have these like for the math people, your representations. So what we're doing. Okay, sorry. So there is a notion of Fourier transform. So there is a natural notion of Fourier transform for groups to the real numbers or the complex numbers. But it turns it turns out that sort of your frequency modes, in a sense, are the irreducible representations of your group. So you can sort of decompose any function from the group to the real line into functions from irreducible representations to the real line. And it turns out that the same thing holds if you have functions, or a similar thing holds if you have functions from the group to some set of matrices, or in our case, superoperators. But instead of I'm not going to go into the details of this too much. So there is this object called the Fourier transform of psi, which I'll denote fancy f of psi, of phi, and it takes an irreducible representation of the group sigma, and it sort of maps it to this sort of tensor product operator. If you want to know more about this, there is a really nice sort of semi-review paper by Timothy Gowers and Hatami, which goes into a fair amount of detail on how this thing works. But I'm just going to take out two things that you would expect from a Fourier transform. One is that it has an inverse. Namely, the inverse just comes from partial traces somehow. And you can compute for yourself that this is actually going to come back to phi of g. But more importantly, it has a convolution property. Namely, that if I take the Fourier transform of a convolution, it becomes the product of the Fourier transforms. And this is, this is why you like Fourier transforms. But if you don't believe that this actually should be called a Fourier transform, you can just think of it as a bunch of abstract objects that have a correct property. Because the nice thing is, we can now take our randomized benchmarking data and sort of plug in the Fourier transform and the inverse Fourier transform, and then the convolution becomes a power. And now we have here the power of a matrix. And this, if any one of you have ever done sort of like an undergrad course of sort of computational physics, you know that a very useful trick is that if you want to find out what the largest eigenvalue of a matrix is you just take a whole bunch of powers of it, and eventually this matrix will start to behave as sort of a single exponential with the decay rate set by the largest eigenvalue. So here you should already sort of recall that that what we want is that this data sort of looks like a linear combination of exponentials. And we sort of already have a justification for this now, because if you look at it in the Fourier transform picture, what you see is that what randomized benchmarking does is just taking a bunch of powers of matrices. So what you should see show up is somehow the largest eigenvalues of these matrices. And now we can make this a little bit more rigorous by realizing that the ideal implementations, which correspond to representations, their Fourier transforms are actually projectors. And this is something that's actually fairly easy to prove, but I'm not going to do this. And then the idea is that if you want to make this notion of, oh, what we are measuring is really the largest eigenvalue of somehow these Fourier components, if you want to make this rigorous, is you're going to think of your actual, like the Fourier transform of your implementation map as a perturbation of the Fourier transform of your ideal implementation, which is omega. And because this thing is a projector, it has sort of top eigenvalues that are 1, and all the bottom eigenvalues are 0. And if we take a small perturbation of this, or a perturbation that's not too large, what we should have is that these Fourier transforms, sort of evaluated at each representation, should look like a matrix that has a few really large eigenvalues and a bunch of really small ones. And in particular, the rank, this is a technical bit, the rank of these sort of Fourier transformed representations in the ideal case is going to correspond precisely to how many copies of sigma show up in omega. And in many cases, this is just 1. So for your convenience, you can just think of this as this sort of ideal thing as just being a rank 1 projector. And then you can sort of think that you can start doing, now you can start doing perturbation theory. So you can start saying, oh, I'm going to write this, this Fourier transform matrix as some dominant eigenspace, which has a rank, sort of the number of irreducible subrepresentations associated to sigma, and some small and exponentially decaying sub-bit. And now there's a whole bunch of technical things that you need to do. Namely, you have to do 2 things if you want to make this perturbation argument rigorous. One is you have to find a good norm in which you want to do your perturbation. You have to define what you mean by close, and you want this to be somehow relevant. And this took a little bit of work. And then you have to do some slightly more sophisticated perturbation theory, mostly because these Fourier transformed matrices are generically not normal. So you have to do a whole bunch of things with making sure that the eigenvectors are well conditioned and stuff like that. But this all works out. And it turns out that the correct way to think of a norm on these sort of Fourier transforms is directly given by sort of the average diamond distance between your implementation map and your ideal implementation, so your sort of your reference. And if this thing is small enough, so it's on the order of 10%, so sort of an awkward number, I think in reality it's larger, then you can guarantee for any possible implementation map that satisfies this, that the randomized benchmarking data is close to a linear combination of exponentials, where these sort of little m's are your exponentials, up to a number that goes down exponentially in this distance. So if you go out, if you take m to be larger than say 5, then the distance between these things is going to be extremely small. So there's two things to notice here. One is that these matrices M sigma correspond to somehow the dominant subspaces that we talked about before. They're really the Fourier transforms projected onto their largest eigenvalues. And these the largest eigenvalues, the number of these precisely corresponds to how many copies of this irreducible representation show up in your reference representation. So this is one of the things that we noticed, is that this sort of folklore knowledge that randomized benchmarking should give a linear combination of exponentials is only true if there are no sort of multiplicities in the sort of ideal representation. And this is often the case. If you pick a standard group, then this almost never happens. Like for the Clifford group has no multiplicities, the Pauli group has no multiplicities. But there are a couple of examples where this is non-trivial. And then these things start having sort of distinctly non-exponential behavior, because now we're taking a power of a matrix, and a power of a matrix can, at least in the short term, not look like an exponential at all. But if there are no multiplicities, then we get sort of the nice result. And this holds for any randomized benchmarking statement. And it also gives you sort of a nice interpretation of what is going on here, at least analogously. So you can think of somehow the exponentials that come out, you can sort of think of them as sort of the frequencies associated to different representations that are present in phi. So I can sort of write my phi as a combination of different representation modes in the same way that I can decompose an arbitrary signal into sinusoids. So this is really what randomized benchmarking measures. It sort of measures how much of each representation is present.
Jonas, maybe
yes,
you touched on this, or I missed the point,
Mm-hmm.
but given a group, the representations take values in matrices of certain sizes. So this map phi might map to matrices of a size for which there is no representation.
Yes. Yeah.
So maybe you can you repeat?
I was actually about to get into this. This is a problem, and this is the reason. This is one of the reasons why you have to pick a diamond norm here, because this is sort of a worst case norm. If you pick other norms, then you might run into situations where phi is actually somehow close to a representation in a dimension where no representations exist. In a mathematical sense, this is sort of a stability theorem type thing, and this strongly depends on what norm you pick. So this is one of the things that we thought about, and one of the things that is actually folkloristic is that there is a good reason why we have to pick the diamond norm here. Because for instance, we can try and do the same thing with a promise on the average fidelity between our implemented gate and the ideal gate. So we could say, like folkloristically, when people say close, what they mean is that these gates have high average fidelity. So what you could say is okay, let me pick another sort of metric of closeness, which is I want the average fidelity over my gates to be larger than 1 minus delta. And I could hope that I could sort of get the same thing, that my randomized benchmarking data is still well described by a linear combination of exponentials associated to the sub-representations of omega. But it turns out that this is not the case unless delta is exponentially small in the number of qubits. So unless you pick this thing to be extremely close to 1, this doesn't work. And the way you do this is you can sort of construct counterexamples. And the thing is, like, the magic trick here is that if you are allowed to pick arbitrary implementation maps, is that you can somehow condition the behavior of these maps on you having a state that lives in a small subspace. So what I've written down here is an implementation map that does the following thing. First, it does a measurement, a projected measurement, onto some small subspace of dimension large L, which is, we're going to choose much smaller than the ambient dimension. And if this measurement clicks, so if the state is in this subspace, I'm going to apply some small quantum channel that preserves this subspace. So you can think of it as, let's think of it as just an abstract thing. So it keeps the state in this corner of Hilbert space. And if the measurement doesn't click, then I'm just going to do my gate perfectly. So you can check that for all G, this is a nice, perfectly functional quantum channel. And in particular, you can also check that the average fidelity is going to be larger than 1 minus 2L over D, where D is sort of the ambient dimension of your Hilbert space. So typically, D is 2 to the Q. So if I pick L to be a constant and I take D to be really large, which I can easily do by just adding the number of qubits, I'm going to have a fidelity, an average fidelity that is arbitrarily close to 1. But if I actually look at my randomized benchmarking data, I'm going to see that if I start with an initial state that is in this sort of small subspace, then the only thing I'm ever going to do is apply lambda. So instead of this nice convolution, I'm just going to have an m-fold power of some superoperator. And an m-fold power of some superoperator can give you essentially arbitrary behavior. So we can have a map, an implementation map that has extremely high fidelity. Not even on average, but actually for all of these G's, the fidelity is extremely high. But the randomized benchmarking data, at least if I pick the right initial state, is going to be completely uncorrelated from this. And sort of the message from this example is that if you want randomized benchmarking to work, at least in a large number of qubits, you need to somehow promise that the gates that you start with are close to what they're supposed to be in the Diamond distance. So it's sort of pessimistic. And what this tells you is that you really can't do any better. You can't expect that your gates are good on average and still have correct behavior of randomized benchmarking. And this is like, I think this is sort of an issue, and I think it's sort of underappreciated, that if you do randomized benchmarking on a high number of qubits, you have to make a fairly strong promise on the initial quality of your gates in order for your data to not be gibberish at all. Which is sort of, I think, sort of a non-trivial statement, and I think something that has been underappreciated. And there's going to be some people that are going to be angry at me for saying this out loud, because it sort of undermines the basic rationale of average randomized benchmarking, is that it works for a large number of qubits.
But what it does mean is that it would work for a large number of starting states.
Yes, yeah. But you can also so for a generic starting state, this is going to work.
But of course, that's not what you're interested in when you want to do a computation, right? You have a very specific starting state.
Yeah, and I mean, I can also twiddle this L, right? I can pick its square root of D or anything that grows slower than D, and now I can make really arbitrary behavior for high fidelity for a large subset of states. I mean, still exponentially small,
exactly,
but
yeah.
it's not like it's going to be a fairly large set. But yes. So you're not interested in have a procedure that works well for a generic state. You would like it to work well for almost all states, or even all states. It's a little bit contrived, right? Because in practice, this never happens. It's very malicious. You have your quantum computer is doing a measurement that has an exponentially small probability of success, and then conditioned on that success, it's going to do something very malicious. But it, you know, it could happen.
Actually, you want it to be correct on a very small set of states, namely those that come up in computation.
Yeah, yeah,
You don't care if it's right on a generic state, but you want it to be correct on the ones that you see, or, you know, that you generate during your computation.
If this piece of Hilbert space is something that you're interested in, then you're in trouble.
But isn't it that you're checking sort of if your hardware implementation works, which means you want it to work for all kinds of algorithms, and each algorithm has a set of input states that you want to act on. So
yeah, but these are
you don't want to
not
restrict to one sort of small corner of input states.
Yeah, but this small corner of input states might be really important. I think the more important point here is that if you want to believe that randomized benchmarking is going to work well because you have some prior on your fidelity, like some constant prior that you can then update, you have to make additional assumptions on your noise, namely that it doesn't do these kind of malicious things. And this is sort of a refinement of what has been known before. I don't think this is the ultimate theorem, but it somehow sets a limit on what you can do without making structural assumptions on these implementations. All right, so that's sort of a positive and a negative result. And then finally, I want to sort of quickly talk about how this sort of looking at randomized benchmarking as sort of the power iteration method in frequency space. It also gives you some really nice ways to, once you have these probabilities, to sort of learn more detailed things about them. So one of the things, so you have this sort of probability data that depends on these linear combination of matrix exponentials. And one of the things that you might care to do is isolate the frequencies associated to a single representation. One is because it makes the fitting easier, because if you have to fit like a lot of exponentials, this is typically quite hard to do in practice. So you want to sort of try and fit a single exponential because you can do that. It's easier to fit. So one of the things you could try to do is, because it's quantum mechanics, everything is linear, you can just take different p's for different values of g's or g or something, and take linear combinations of them to try and make these sort of prefactors cancel out for all sigmas that aren't the one you're interested in. And if you think of these m's as a frequency, you can sort of think of this as like, oh, we want to put a filter on our data. So this is sort of the way we try to think about this, is like, okay, what if we think about, if we take this sort of frequency analogy seriously, can we think of these post-processing methods, of which there are a bunch, less than randomized benchmarking, but still 5 or so. In particular, you can think of linear cross-entropy benchmarking, which is the thing that Google does in their supremacy paper. You can think of it as randomized benchmarking plus some frequency comb filter, which I think is kind of nice. And I don't think anyone has sort of noticed this before, but it sort of falls out of the framework that we have if you think of RB as being sort of a signal processing method, a non-commutative signal processing method. So what we're going to do is basically we're going to write down the fact that you can, that a Fourier transform matrix, you can sort of pick it out by, these things are somehow, if you do signal processing with sinusoids, one of the core features of sine waves is that they're orthogonal to each other. So you can sort of pick one out. They form a basis in a sense. And this is true for these, this is true in the general case as well. So somehow if I multiply my data with a particular function of my representation, I can pick out the frequency associated to that representation. So a thing I can do is I can take my randomized benchmarking data, P of G of M, and for many G's, so these end gates here, and I'm going to multiply it with a matrix element from the irreducible subrepresentation associated to the frequency that I'm interested in. So you can think of this as sort of an inner product in G space. So it's a sum over G and two vectors and I guess the group algebra for people that care about these things. And it turns out that multiplying your data with these kind of numbers, and here I picked a particular matrix element, so the one associated to our input states and our output POVM, and this is going to be important later. But in principle, I could have picked any matrix element of this representation, and I would have gotten the same result, just for a different A. So we can compute this sort of K of M, which corresponds precisely to the frequency associated to this particular representation. So we can sort of isolate these poles. The problem is that the thing that we've done is not necessarily efficiently estimable, because we've sort of gathered this exponentially large amount of data. Like we have to gather data for all of these G's, and the size of your group can grow exponentially in the number of qubits. So we have to somehow figure out a way to estimate K of M with much less data. And it turns out that this is not always possible, because the function that you're multiplying it with this is not a probability anymore. So you can sort of run into sign problems. So this was sort of a tricky thing, and thus far no one had really been able to find out a way to do it that works for all groups. So all of these previous papers essentially make some assumptions on the types of groups that these kind of procedures work for. But it turns out, so one of the things you can do is you sort of randomly select these G's, and then you estimate the local probability. And because you're taking an average over G, you hope that this average can somehow estimate its mean efficiently, but then you have to control the variance. And it turns out that you can control the variance if this POVM has a special property, namely that it's a tree design. Why tree design, you ask? Well, I don't know. This was somehow a surprise, but this works. It's a sufficient condition. But it turns out that you can sort of find tree designs relatively easily. So you can take the computational basis and then apply a random Clifford to it and then measure in that basis. And then if the set of all of those bases will give you a tree design. And sort of a nice little feature of this estimation procedure is that you don't have to measure this POVM all at once. You can just flip a coin and measure one of the bases, and that'll actually work as well. So you never have to actually implement this tree design. You only have to sort of be able to implement all of the bases that make up this tree design. This is also a sufficient condition and not a necessary condition. In particular, if you go look at the linear cross-entropy benchmarking paper, there they only ever measure in the computational basis. So they don't have a tree design, but it's still like their frequency, which they call FXEB, is still efficiently estimable. And the reason for that is somehow because they're doing higher random unitaries, the randomness in the gates that you're doing somehow effectively creates this tree design, because relative to the gates that you're doing, you're measuring in a random enough basis. But this is all like, it's not quite clear what the limits of this are. There is a really nice connection, which is sort of where I got the tree design idea from, to a strand of research called shadow tomography. So people have been thinking about ways to estimate, do sort of efficient tomography procedures. So like if you have an exponentially a state, it takes an exponential amount of measurements to reconstruct the entire density matrix. But if you're only interested in like estimating the expectation value of that density matrix with respect to a really large number of observables, then it turns out that that can actually be done with a polynomial number of measurements. In particular, there's a really recent paper from the Presco group where they prove that if you just measure your state enough in random Clifford orbits, like computational bases set by random Clifford orbits, the resulting data is enough to form sort of a shadow tomography scheme that is efficient. So somehow the fact that it's a 3 design is important for scalability in the sample complexity sense, like you being able to estimate these things efficiently, both in randomized benchmarking and in shadow tomography. So there is something about 3 designs, and I'm not entirely sure what it is. I'm quite happy it's a 3 and not a 4, because 3 designs are easy to make and 4 designs are really hard to make. All right, so I think I'm gonna make it towards the end somehow. So what have we done? So we've formulated a general scheme, sort of meta scheme for randomized benchmarking, composed of 2 parts. One is a data gathering procedure, and one is sort of a post-processing procedure once you have the data that covers literally every randomized benchmarking paper. I think we actually cover all of them, and there's about 37, yeah. Which I think is quite nice. It's sort of a unifying effort. It turns out that these things are all the same. This also means that we can stop writing papers where we pick a new group and declare randomized benchmarking, because now we've sort of covered everything. We proved a general sufficient condition for proper behavior, namely that it goes as a linear combination of exponentials. We've also sort of argued that if you don't assume this, but assume something weaker, then it doesn't work. And then we formulated sort of a general post-processing scheme that allows you to pick out these single exponentials, which is efficient if the POVM that you start with is a 3 design. So the question is now, which is something I really want to do, is can we take this signal processing analogy further? Because now we're doing what you can think of randomized benchmarking as sort of taking your implementation map and filtering it with itself. And you can think of these character post-processing schemes as sort of putting a window filter around your particular representations that you're interested in. But, you know, nothing stops you from putting other kinds of filters on these maps. So maybe we can learn interesting sort of aspects of our quantum computers by putting different filters on this kind of data, or gathering our data in a different way to different filtering schemes. And then, like, one of the things that I'm really interested in is somehow we're sort of getting a shadow process tomography scheme. This is really not clear to me. Like, somehow the fact that we have this analogy with shadow state tomography. So shadow tomography really only works for states now. And I'm wondering if we can sort of take the thing that we have right now, which is randomized benchmarking, in a sort of scalable post-processing scheme, whether it somehow generalizes all the way to a method that allows you to efficiently predict linear quantities of your maybe your implementation map, or just a general super operator, without having to actually reconstruct the full super operator. So this is a thing that I want to sort of figure out in the future, but I'm not really sure how to do it yet. All right. Thank you all for listening.